Very good morning to all of you. I cordially welcome you all for this engineering thermodynamics course. So the today's classroom discussion topic is the Joule-Thomson coefficient, and similarly, how can we define the inversion curve? How can we define the Joule-Thomson coefficient and Vander Waals equation of the state? So the motivation is why we have to study this Joule-Thomson coefficient and inversion curve. So it is very essential to know that why some of the gases will produce heating effect during the expansion process. That is, normally we think that whenever a gas is subjected to the expansion process, all the gases will give you only the cooling effect. But it is not 100% correct. So some of the gases will also produce heating effect whenever they are subjected to the expansion process. It seems to be very irrelevant, but whenever you are talking about the Joule-Thomson coefficient and inversion curve, you can understand the beauty of the inversion curve. So why it is important, one is because nowadays we are frequently talking about the cryogenic technology. So cryogenics is nothing but it's the production of lower temperatures. So that is whenever you are launching the rockets or the missiles from the DRDO or from the ISRO. So this cryogenic technology is very important one. So if you want to thoroughly understand the cryogenic technology, that is how we are liquefying the various gases. That is, we are using the liquid hydrogen, liquid helium, liquid oxygen, liquid nitrogen. So that is why we are liquefying the gases. So that is very important, beautiful concept in the cryogenic technology. So that is the motivation behind this Joule-Thomson coefficient and inversion curve. So as usual, every lecture should have the objective and similarly the outcome. So I am expecting two outcomes out of this present lecture. The first one is you should be able to explain the Joule-Thomson coefficient with the help of a property diagram called pressure and temperature and demonstrate the importance of inversion curve in the cryogenic applications. And the second outcome I'm expecting from you is, so make use of the Vander Waals equation of the state, examine the behavior of the real gases. So now let us go to the Joule-Thomson coefficient, that is the experiment. So this experiment is known as the Joule-Thomson porous plug experiment. Porous plug experiment. So that is, it is basically taking place according to the throttling. So throttling is nothing but, so it is a enthalpy, that is a constant enthalpy. Throttling means it's a constant enthalpy process. It is an irreversible expansion process. So it is very important question in the GATE examination. During throttling process, dash parameter will remain constant. That is, the enthalpy parameter will remain constant. So it is always expansion according to the irreversible process, because all the processes are taking place according to irreversible in the nature only. So now here we can define the Joule-Thomson coefficient in such a way that mu is equivalent to dt by dp at constant enthalpy. So that is the definition, and the formula of the Joule-Thomson coefficient is very important one. So mu is equivalent to dt by dp at constant enthalpy. So why you are keeping it as constant enthalpy means because it is a throttling. Throttling means constant enthalpy. So that's why H will remain constant. Then why you are writing down it as the dt by dp? So that is to understand why you are writing down dt by dp. So just we have to consider a property diagram called temperature versus pressure. So that is whenever you have drawn a temperature versus pressure diagram, so how can we find out a slope? How can we find out a slope at any point? So on this particular TP diagram. So that is nothing but slope is nothing but is a dy by dx. So dy by dx is the slope, you aware that. So here y-axis we are having the temperature and x-axis we are having the pressure. So the slope at any point of this particular curve is equivalent to dy by dx, that is equivalent to dt by dp. dt by dp. So now all these are the constant enthalpy lines. All these are the constant enthalpy lines. So that's why, so whenever we are going to the previous slide, so here I have written is a dt by dp, that is nothing but is the slope of TP diagram. Slope of TP diagram. So dt by dp at H is equivalent to constant. So mu value is equivalent to 0 for an ideal gas. It is important. For an ideal gas, what is the value of the Joule-Thomson coefficient? It is equivalent to 0. So now, so just you understand, because it is a very, very important diagram, very, very important diagram. So it is the TP diagram. So this particular the dashed line, this particular the dashed line, it is known as the inversion curve. It is known as the inversion curve. That is, it is locus. It is the locus of all these particular the inversion points. Is the locus of all these particular inversion points is known as the inversion curve. That is, just you observe here. So whenever you are having a throttling process, so that is the slope is increased up to this particular extent, then it is gradually falls down. Then when you take the another isenthalpic process line, so just you observe the isenthalpic process. So up to this, there is a increase in this particular the slope, then there is a decrease. And similarly, you consider the another isenthalpic line. Up to this, you can find out the rise in the slope, then it is decreasing. So that's why whenever you are joining all these particular the peak points of the curve, so whenever you are joining all these particular the peak points, then it is formed as the inversion curve. It is known as the inversion curve. So why the name is given as the inversion? And what is the value of the Joule-Thomson coefficient on the inversion curve? Just now I told you that for an ideal gas, so you take any point on the inversion curve, mu value is equivalent to 0 for an ideal gas. Now, what is the beauty here is, so this inversion curve is basically separating the gases into the cooling region as well as the heating region. Whenever there is an expansion process, so that is the normal tendency is that whenever the gases are subjected to the expansion process, pressure will be decreases and temperature will be decreases, so that we are able to obtain the cooling effect. That is the normal assumption. But here, so this inversion curve is basically discriminating into the two regions, that is the gases which are producing the cooling effect during the expansion process, the gases which are producing the heating effect during the expansion process. So that is the inversion curve. It is basically discriminating the gases which are falling either under the cooling region or under the heating region. So here, under this particular the cooling region, the mu value is always positive. Mu value is always positive in the cooling region, because it's a very, very important concept in the competitive examination. So in the cooling region, what should be the mu value? So mu value is always greater than 0. Why it is greater than 0? Why it is greater than 0? And why it is less than 0 in the heating region? Why it is less than 0 in the heating region? So just to observe here, as pressure increases, what is happening to the temperature? So as pressure increases, temperature is also increasing. So the formula is mu is equivalent to dt by dp. So numerator is increasing as well as the denominator is also increasing. So the resultant effect, you are able to get it as a positive effect. So the positive effect is nothing but in the cooling region, the mu value is always positive. That is, the gases which are able to give you the cooling effect during the expansion process are basically lying in this cooling region only. So now let us consider this particular the heating region. Now the pressure is increasing. Now what is happening to the temperature? Now the temperature values are gradually decreasing in this direction. Now they are decreasing in this direction. So as the pressure is increasing, the temperature values are decreasing. So dt by dp value will become negative. dt by dp values become negative because the numerator is decreasing, denominator is increasing. So the resultant effect is negative. So that's why the mu value, Joule-Thomson coefficient value is negative in this particular the heating region. So the same thing I have written here. The region inside the curve, inside the inversion curve, it is inside the inversion curve. It is known as the cooling region. Since mu is positive, temperature falls with fall in pressure. So the same thing I've explained here. So when the pressure is increasing, temperature increases. When pressure decreases, temperature decreases. That's why you are able to get cooling effect. And similarly, the region outside the inversion curve. So it is the inversion curve outside region is known as heating region. So in which you are able to have the mu value as negative. So temperature rises with fall in pressure. So now you can see here when the pressure is decreasing, the temperature is increases. Or when pressure decreases, when the pressure increases, the temperature value decreases. So here the cooling can take place only if the initial temperature before throttling is below the maximum inversion temperature. That is, if you want to obtain the cooling effect, so the gases should lie in this particular cooling region. Suppose a gas is falling in the heating region, then you have to decrease the temperature of that particular the gas below this inversion temperature, then only that particular the gas will give you the cooling effect. So that is the very important aspect. So here I have listed down some of the inversion temperature values of the various gases. Like helium, you are able to have the 24 Kelvin, hydrogen 195. So like that, air, nitrogen, argon and carbon dioxide inversion temperature values are given to you for your reference. And then the second topic here is the Vander Waals equation of the state. And I've already told you that this Vander Waals equation of the state will coming into the picture whenever we are dealing with the real gas behavior of the state. So because in the ideal gases, we assumed that there are no molecular forces of attraction and repulsion among the gaseous molecules, and similarly the volume occupied by the individual molecules can be neglected as compared to the total volume of the system. But these two are very essential whenever you are considering the real gases behavior. So that's why A by V square, because the A is basically taken, is the A and B are the constants. So A and B units are very important ones. Sometimes he asked the A and B units of the Vander Waals equation of the state. So A units are Newton meter to the power of 4 by kg mole square, and B units are meter cube per kg mole. So that is why how you obtain this particular equation means normally the general gas equation of the state describes PV is equivalent to RT. So here we are adding A by V square to the pressure and we are subtracting B from the V. So why we are doing this? That is, we have to consider always the forces of cohesion or repulsion among the gaseous molecules. So A by V square term is basically taking care about how many molecules are basically under the attraction and repulsion. And B, so B is nothing but is a co-value. So that is the value occupied by the individual elements is to be considered. So that particular one is basically taken care by B. So that's why the Vander Waals equation of the state is modification of the general gas equation of the state. So P plus A by V square into V minus B is equivalent to RT. So the units of A and B are very important one. So what are the various the gate questions which were asked on this particular one? That is the Joule-Thomson coefficient is defined as, because you know that mu is equivalent to dt by dp at constant enthalpy. And the second question is the Joule-Thomson coefficient value on the inversion curve is, it's always 0 for the ideal gases. So like this we can have the topic on this Joule-Thomson coefficient, inversion curve, Vander Waals equation of the state. I hope you understood the concept of the Joule-Thomson coefficient and inversion curve, because these are very important one in the cryogenic applications. So thank you very much for attending this important lecture on the inversion curve, Joule-Thomson coefficient and Vander Waals equation of the state. Thank you very much.